All right, now we're going to do a fun one. This next one that we're going to use is called Newton's Law of Cooling. And I'm sure you have heard of Sir Isaac Newton. All right, and here's what it says. It says that the temperature of a heated object decreases exponentially over time toward the temperature of the surrounding medium. So you take a pizza out of the oven. When you first take it out, it's at 375 or 450 or whatever you cooked it at. You leave it in the room, and if you leave it there long enough, eventually it's going to be the same temperature as the room, right? And it says the temperature U of a heated object at a given time t can be modeled by the following function. And this one was kind of an ugly one. U of t, so the temperature at any given time, is equal to capital T, which is the constant temperature of the room or whatever's, an ice bath, if you put it in an ice bath, whatever, T, plus the original temperature minus the temperature of the room times E to the KT. And K is less than 0 because it's cooling. So this is the temp of the surrounding medium. I'm going to put room because that's the only way we're going to use it. U sub naught is the original or the starting initial temperature, the initial temperature of the heated object. K is less than 0, so it's a constant. In this case, it will be negative. And the little t is how long, is just time. Okay? So, turn to the back. And I'm going to show you the way this equation is used. We have a memo. It says, to Detective Sergeant, it says, the elevator operator of the Ritz Palace Hotel died from a stab wound while on duty last Thursday evening. His body was discovered at midnight by a family on its way down to the pool. This is gruesome. When we arrived at the scene, we canvassed the area but found nothing. The elevator is full of fingerprints of the hundreds of guests who ride it during the day. We have several suspects in mind, but we are having trouble pinning down the time of death. If we can determine that, we have a good shot at finding the killer. And so this formula is really used in forensics to determine time of death, and that's what we're going to do. So it says paramedic report. The date was 10/05/2005. The time the body was found was exactly midnight. Of course it was. The body temperature at midnight was 80 degrees. So obviously, since your normal temp is 98.6, it was dead for a while. The body temperature at 2 a.m., they took the temperature again, was 75 degrees. And notice, there's a note there, the elevator temp was cold. It was set at 60 degrees. So that's your temperature of the room, okay? First, it says recognize that you are working backwards in time. So you're starting with the now and working back to the time of death. So we're going to begin with the body temperature at 2 a.m. as your first value. And we're going to work backwards to find out the time of death, the T. And we're going to start with that initial value of the temperature at 2 a.m. in order to get our K. So in part A, we're going to say U of 2 hours after it was found, the temperature was 75 degrees Fahrenheit. Okay? The temperature, big T, of the room surrounding was 60 degrees Fahrenheit. The original temperature when they first found it was 80 degrees Fahrenheit. And our job is to use that information to find K. This is actually a pretty easy equation to work with. So we're going to substitute everything in. Let me just tell you something. If you don't make a little list like this, you're going to have a hard time figuring out what pieces are what. All right? So U of T, which was our original equation that we're using, U of T, here we want U of 2, it's 75. So we're going to go 75 equals the big T, which is 60, plus, parentheses, the initial temperature that when we first measured it, which was 80, minus the temperature of the room, which is 60, E to the K we don't know, but we do know T, it's 2, so I'm going to put 2K. So this right here is my U of 2, okay? And there's my 2. So I've got 75 equals 60 plus 20 20e to the 2k. I'm going to subtract a 60 from both sides, and I have 15 equals 20e to the 2k, divide by 20, and 15 divided by 20 is 3/4. So 3/4, or 0.75, equals e to the 2k. Take the ln of both sides to make the e go away. ln of 3/4, or 0.75, however you want to think about it, I'm going to leave it like that, equals 2k. Well, I want k, so we're now going to divide by 2. And you get k is equal to ln of 3/4 all divided by 2. So we did the first part, we found k. Okay? Now the second part is, we still want to know what was the time of death. So we did this first piece in order to find k, but now in our formula we know the k. It's right here. What we're going to do is we're going to say the temperature of the live guy, okay, right before he was killed, providing he wasn't sick, was 98.6 degrees Fahrenheit. Now I realize not everybody has that as their normal temperature, but we're going to make that assumption. Big T is still 60 degrees, temperature of the room. Now, our initial temperature is 80. That's what they found the body. And what we're trying to find now is find T using the K that we found in part A. So here's the original equation again. It was U of T equals big T plus U sub naught minus big T e to the KT. Okay? But now we know this. It's 98.6, so 98.6 equals big T is 60, U sub naught is 80, minus 60, this part's the same, e to the, now we don't know T, but we know K. So we're going to go ln of 3/4 over 2 times T. So we're going to subtract a 60 from both sides, line up decimal points, and you get 38.6 equals 80 minus 60 is 20. E to the ugly stuff, 3/4 over 2 times T. Okay? Divide all of that by 20. Divide by 20. When you divide that by 20, you get 1.93 equals E to the, again, ugly stuff. We don't care how ugly it is. Doesn't matter. Calculator's doing the work. Take the ln of both sides to get rid of the E. And you have ln of 1.93 equals ln of 3/4 over 2 times T. How do we get rid of that? Multiply by its reciprocal. So we're going to multiply by 2 over ln of 3/4. That will all cross cancel. Multiply this side by 2 over ln of 3/4. I'm going to put 7.75 for 3/4 since it's a decimal in the numerator. It matches. And what we have is T equals 2 ln of 1.93 over ln of 0.75. Now, put that in a calculator and here's what you're going to get. Negative 4.57. But remember, we're looking for the time of death. They found the body at midnight. So what we want to know is, what is midnight take away 4.57 hours? This is not 57 minutes. It's 57 hundredths of an hour. So we want 4.57 hours before midnight. That in and of itself is kind of hard. So let's just do the 4 part first. So 12 o'clock midnight, take away 4 hours, would be 8 o'clock. Now we're going to start with 8 o'clock, and we have to figure out how many minutes is 57 hundredths of an hour. Well, I just gave you the answer when I said it. 57 hundredths of means multiply. An hour is 60 minutes. Okay? I can divide this by 20, divide this by 20, do all that in the calculator, and you're going to get 34.2 minutes. Let's just round that off to 34. So what we want to know is, what is 8 o'clock take away 34 minutes? Take away 34 minutes. We'll just run it backwards. 8 o'clock take away 30 minutes would be 7:30. 4 more minutes would be 7:26 p.m. That is the time of death right there. Now to find out who did it, you found out who's in the elevator at 7:26 p.m. Or you could just watch the video and watch and see who killed him. That's a good problem. All right, so those are growth and decay models that we've done. We're going to look now at what's called a logistic model. A logistic model is more a population model that you're used to, not bacteria, but population models of animals and people and things where it can't just grow forever because they run out of food or they run out of water, or so the growth levels off. So it doesn't just continue to increase or decrease, it levels off. And that formula is a little more complicated. The population in a logistic model at any given time is equal to C, we'll talk about that in a minute, over 1 plus AE to the negative BT. Now, there's a lot of letters in there, okay? A, B, and C are constants. C is greater than 0. If B is greater than 0, it's a growth model. If B is less than 0, it's a decay model. So this is growth. This is decay. And we're going to talk more about those letters. Just hang on, okay? So let's kind of take a look at what that model would look like. Here's a growth model. This point right here is at time 0, you have a population of some amount, P of 0. And it starts growing, and then it changes and it levels off because of some circumstances like food or water. And it levels off and it never grows more. It just stays level. Okay? Right here, see here I was increasing and then it changed right there. And it's kind of hard to see. But we call that point an inflection point. And the inflection point is the point on the graph where the graph changes from being curved upward, like it is here, to being curved downward. Only I'm kind of exaggerating it. And it's always at 1/2 what we call the carrying capacity. The carrying capacity, it means that's the max the population can reach given the circumstances before it can't grow anymore. So this is a line, y equals c. It's just a carrying capacity. So this is a growth model. It grows only so much and then it can't grow anymore. Let's look at what a decay model would look like. Okay, so here's your initial population at time 0. There's P of 0. All right. It starts decaying, but rather than it being like the uninhibited decay, it changes and it reaches a bottoming out point and it won't decrease anymore. And there's an inflection point here too, where this is curved up and then it's curved down. It's hard to see, but that inflection point is always at the point 1/2 C. Okay, and we still have a line of y equals c for our carrying point, or carrying capacity, excuse me. Actually, this is y equals 0. This line up here is still considered y equals c. Alright, so in the middle of your notes you'll see some properties of the logistic growth function. It says the domain is the set of all real numbers. The range is the interval 0 to c, where c is the carrying capacity. There's no x-intercept, so it never touches this x-axis. The y-intercept here and here is P of 0. There are 2 horizontal asymptotes. Here it is y equals 0. It never touches that, okay? And here it's y equals c. I showed you that on both of them. And there's an inflection point at 1/2 the carrying capacity. So let's look at an example. It says fruit flies are placed in a 1/2 pint milk bottle with a banana for food and yeast plants for food and to provide a stimulus to lay eggs. There you go, something you didn't know about fruit flies. Suppose that the fruit fly population after t days is given by this formula. P of t equals 230 over 1 plus 56.5 e to the negative 0.37 t. I know, it's kind of ugly, isn't it? It says state the carrying capacity and the growth rate. All right. Carrying capacity means that as time keeps moving on, in other words, as time approaches infinity, as t gets bigger and bigger and bigger and bigger, then what would happen in this equation is down here we have e to the negative 0.37t, and as t got bigger and bigger and bigger and bigger, this approaches 0. It gets close to 0 as time goes on. Because if you think about it, it would be e to some tiny, tiny, tiny number. Negative 0.37 times a million. Okay, it would be a teeny, tiny little number, so it would be close to 0. Which would mean what you would have is you would have 230 over 1 plus almost 0, which is 230 over 1, which is 230. Therefore, 230 is your carrying capacity. Okay? Right there it is. The growth rate is right here. It is our B, and it is the absolute value of negative 0.37 shown as a decimal, so it's 37%. That's how much it's changing per day. So that's part A. Then it says part B, determine the initial population. That means what is P of 0? So let's figure that out. That's the initial. P of 0 would be 230 over 1 plus 56.5 e to the negative 0.37 times 0. Well, anything times 0 is just 0. And then you would have e to the 0, which is just 1. So you would have 230 over 1 plus 56.5 times 1, which is just 230 over 57.5, which when you divide that out is 4. So you start out with just 4 flies. I know, fascinating, isn't it? I like the murder one better. Then let's look at C. It says, what's the population after 5 days? Well, obviously that means what is P of 5? So we would have 230 over 1 plus 56.5 e to the negative 0.37 times 5. You're just going to put that in the calculator, you guys. And you're going to have it's approximately 23 flies. There's people that actually do this, study this fly business. Okay, D. How long does it take the population to reach 180? It means when is P of T 180? How many days? So we're going to go 180 equals 230 over 1 plus 56.5 e to the negative 0.37 t. Okay. What we're going to do is we're going to multiply both sides by this fraction, the reciprocal of. So you're going to multiply it by 1 plus 56.5 e to the negative 0.37 t over 1. I said reciprocal, I didn't mean that. We're getting rid of the denominator. So you have to multiply the other side by the same thing. 1 plus 56.5 e to the negative 0.37 t. Okay? So then you have 180 times 1 plus 56.5 e to the negative 0.37 t equals 230. Remember, our goal is to get down to the t. So divide both sides by 180. And you have, I'm going to move up here, you have 1 plus 56.5 e to the negative 0.37 t equals, when you divide that 230 by 180, you get 1.2778. Subtract a 1.0000, and you get 56.5 e to the negative 0.37 t equals, subtract the 1, you have 0.2778. Trying to get just the e by itself so you can take the ln. Divide by 56.5. And what you have is e to the negative 0.37t equals, when I divided it, I got 0.0049. And now you can take the ln of both sides, and you have negative 0.37t equals ln of 0.0049, divide by negative 0.37, divide by negative 0.37, and you have t equals ln of 0.0049 divided by negative 0.37, and you get 14.4 days. And by the way, here it looks like you have a positive divided by a negative, but ln of 0.0049 is a negative number, so it is a negative divided by a negative, which is why it came out to be positive. That's a doozy. It's not that it's hard, it's that the manipulations are so difficult. For homework, try problems 1, 3, 7, 11, 13, and 21.